Welcome back to Water Resources. This week we're going to be covering groundwater. This is an important water resources topic. As you recall from an earlier lecture this semester, groundwater is the most abundant freshwater resource that we have available to us on Earth. So let's start out by talking a little bit about some modules that we've already done. During Module 1 we covered groundwater in the hydrologic cycle lecture, the sources of surface runoff lecture, and the ecosystems and physical habitats lecture. Those units all have relevant groundwater related topics that could show up on the quizzes for this module. So I encourage you to pause here and maybe go back and look at the groundwater portions of those previous lectures. All right. We'll bring this, speaking of lectures we did earlier, this is a slide from one of those lectures in Module 1, but I want to start here. First of all, let's define what groundwater hydrology, or what's more commonly called hydrogeology, is. Hydrogeology deals with the occurrence, movement, and quality of water beneath the Earth's surface. Therefore, it's dealing with groundwater. This is a rather interdisciplinary field in scope. It has elements of physical, biological, and mathematical sciences. Most hydrogeologists are trained within the discipline of geology, but the typical hydrogeologist has a pretty deep background in math, sometimes in physics. Some groundwater people specialize in the biology of aquifers, and there is a whole ecosystem that has evolved to live in certain types of aquifers, or the physical aspects. There's also engineering aspects of groundwater that people work with every day. Lots of geologists out there in the geotechnical industry are employed working on one portion or another of groundwater issues, either fully or in part during their day-to-day work. Groundwater, because it is so abundant, as the figure shows here on the center top, groundwater accounts for about 31%, or almost 1/3 of the fresh water we have available to us on Earth. And really, of that other 2/3, most of that's glaciers and ice caps. So this is the bulk of the water we have to work with. So that's why there's so many people employed in this field, and why it's critically important to the welfare of society, and why there's a lot of money invested in it. Well, let's talk about where the groundwater is. The groundwater isn't in an underground lake or in an underground cavern, although it does happen in certain karst settings, but that's not the rule. When we talk about groundwater, what we're really talking about is water that's in the voids or pore spaces in various earth materials. So think about a sediment like sand. When that sediment's in the subsurface, a sand deposit may be deposited by a river or a glacier. Those sand grains don't pack perfectly. There's empty space between individual sand grains. If we turn that sand into a sandstone, make it a bedrock through the process of lithification, the cement that glues those sand particles together may take up some of those pore spaces, but even then there's going to be empty spots between individual grains. So if you look at the the images here, the diagram on the right side of the slide, you see we have in the top sand grains with water in between. In the middle one we have sand grains of various sizes, small, big, and medium, with water in between. Because we have poorly sorted sediment here, meaning we have lots of different sizes, the smaller sediments take up some of the pore space, and there's less overall room left for the water. And then in the bottom we have a sandstone, and so here we have sand grains, but the sand grains are glued together with cement. That's what makes it a bedrock, and the water's in the pore spaces inside this, between the cement and the grains. There's estimated to be nearly 521,000 cubic kilometers. Think about how big a cubic kilometer is of groundwater beneath the U.S. So that's a lot. Now, I've got a little demonstration here. I've got a beaker full of sand, and I put some green food coloring in some water, and I've saturated the sand with that water to sort of show this. And you can see through here we've got the green the green water that is being stored in between the individual pieces of sand that you can see. There are different colors of sand in here: white, red, orange. It's an artificial sand, it's not real sand, but it's the same purpose, same idea. And so that shows you some groundwater right there. If this sand were out in a valley and it were a loose sand like this, and there'd be water stored in those pores. Now, a well, and we'll talk about wells later on, a well is just a tube. Okay, think about a PVC pipe, 3 or 4 inches in diameter, sort of like this cocktail straw, and it's just a tube that we drill down into the aquifer, and then I'm not going to do it because I don't really want to suck up water from this plastic sand with food coloring in it, but you know, if we applied suction here, we would suck the water out. And if we put a little screen on the bottom of this straw so that the sand couldn't get into the straw, but the water could, then we would only be sucking the water out. That's exactly what a water well is. And depending on where you live, it's very likely that your municipal water source, or if you have a private well because you live out in the country, you're using a well to extract water from an aquifer, and conceptually, that's all it is. So let's define the term aquifer. An aquifer is a subsurface zone within an earth material, so bedrock or sediment, that can store groundwater and release it to humans in useful quantities and at useful rates. Now this last part is really important, that can store water and release it in useful quantities and at useful rates. I'll underline that part. The reason this is important is even a shale, and even if you have a rudimentary understanding of rocks, you probably know that shale, which is made out of clay, is fairly impermeable. It's really hard for water to move through shale. So we wouldn't think of shale as an aquifer. If you tried to suck water out of a shale layer in the subsurface, the problem is there's no connection between the pore spaces. So if we look over here at the figure again, if there's no connection between these pore spaces, at least in 3 dimensions, there's no way to suck that water out. If the water's completely trapped and surrounded by cement and grains and not connected to adjacent pore spaces, it's completely stuck in there. Shale actually has a lot of porosity but almost no permeability, meaning lots of pore spaces, but there's very few connections between those pore spaces. So technically, shale is can be a very water-rich rock. But because the pore spaces are not connected to one another, it's almost impossible to suck the water out. Now, one of the other implications of this is if the fluid that's trapped in the grains is oil or petroleum instead of water, you have the same problem. Just like you can't suck the water out, if your fluid is gas or oil, you can't suck the fluid out. That's why they frack. Fracking is essentially causing micro explosions in the shale that create cracks and fissures that connect the pore spaces. You're cracking the rock so that the pore spaces connect and that you can draw fluid out. All right, but that's a little bit of a tangent. So let's move on. Let's talk about aquifer materials. This is building on what we just talked about. A consolidated aquifer material would be bedrock. The consolidated means it's a solid. If you take a hunk of rock, you can hold it in your hand and it won't fall apart. Unconsolidated aquifers are loose sediments, so sands or gravels. In northern Missouri and the upper Midwest, there's a lot of deposits from the glaciers that occurred in the last ice age. Those deposits are not lithified. The sediment particles are not cemented together. They're just loose sands and gravels buried within the earth, so that they're very good aquifers because there's no cement taking up space in them, and some of them are very coarse materials like gravels. They can hold a lot of water and they have a high permeability. So that makes them a good aquifer, because remember, a good aquifer means that it can deliver water for human consumption in a useful quantity. And then we have semi-consolidated. And in our photos here, we have at the top a bedrock aquifer. And here you have solid bedrock, but there's lots of fractures and fault zones and other things going on. And all of those cracks are places where water can be stored and be transmitted. The middle picture here is a deposit of sands and gravels and even some boulders. So this would be an unconsolidated aquifer if it were in the subsurface. And then this is semi-consolidated. I've done a lot of work on islands in the Caribbean on various projects, and I'm very used to seeing this where there the bedrock's so young that it's poorly lithified, poorly cemented. So it's not quite consolidated into solid bedrock like we're used to seeing here in the middle of the continent in Missouri. And you can see here they've just drove the hammer right into it. So it's hard enough to sort of stay together and be cohesive, but poorly cemented enough that you can take a shovel or a pick or even just your hand and sort of scrape the sediment particles out because they're so poorly cemented together. And even in the middle of the continent, we have rocks like this. A famous rock unit called the St. Peter Sandstone stretches through most of the middle part of the U.S. and is a great aquifer. And in many places, the St. Peter's poorly cemented to not cemented at all. It's just loose sand. It's used actually as a source for quarrying sand because you don't have to blow it up or anything else to break the particles apart. You just have to dig it out in a lot of spots. All right, let's talk a little bit about the structure of an aquifer. I'm going to define confined versus unconfined aquifers later, but for now we're going to work on unconfined aquifers, even though you don't technically know what that means yet. First of all, the movement of the water. When we talk about aquifers, we're talking, and groundwater flow, we're talking about movement of water through the pore spaces in the bedrock. There are two zones. There's this unsaturated zone, which we call the vadose zone. It contains both water and air, so it's unsaturated. Here it's the upper part of the aquifer because rain falls on the landscape, hits the ground surface, and then it starts to infiltrate under the force of gravity through the top part of the earth material, whether it's bedrock or sediment, until it reaches the water table. The water table, if we look at this blow up here, this blow up is supposed to be like if we took a small little section out of the water table boundary here and blew it way up till we're seeing individual grains. That's what this inset photo is supposed to be. Here we have the water table. Below the water table, down here, all the pore spaces are filled with water. They are saturated. That's called the phreatic zone or the saturated zone. Above the water table, there is water in some of the pore spaces, but they're not saturated. They're only partially filled, or only some of the pore spaces are filled. And you can see some areas here where there is water contained above the water table. So the unsaturated zone is just that. It doesn't mean it's the dry zone. It's the not saturated zone. There's still water in there. There's still water moving through the unsaturated zone to get to the water table. All right, let's talk a little more about groundwater flow. Already we have alluded to these concepts, but porosity is the amount of voids or pores in an aquifer. So it's the amount of pore space. Usually it's expressed as a percentage, maybe 20% of a given volume of the rock or sediment is empty pore space between grains and so forth. Obviously, the only part of the rock, the only part of the aquifer medium that can hold water is that pore space. So if your rock is 20% porosity, then that 20%, if you multiply that 20% by the volume of the aquifer, if let's just say we had a cubic meter of aquifer and 20% porosity, that means that the volume of water, the capacity of water to be stored would be 20% of a cubic meter, which would be 0.2 cubic meters. Permeability is the ability of water to move between pores. High permeability indicates the ability of water to move rapidly through the aquifer. So the better connected those pore spaces are, the higher the permeability. Right? So if you think about it, a good aquifer, to be an aquifer, you've got to be permeable enough that we can extract water via a well fast enough to supply our needs. If the permeability is higher than that, then it's going to be an aquifer. If the permeability is too low, it won't be an aquifer. It'll be something we'll term a confining unit probably. And we'll explain confining units later. But for now, permeability is how fast water can move from one pore space to the next and how well it can move through the aquifer as a whole. All right, we're going to come back to some of those concepts in another lecture in this module, but as we start to wrap this lecture up, what I want to emphasize here is often we think about groundwater as one system and surface water as another system on the landscape, and we treat them as disconnected. Because we can see streams and overland flow, we tend to think of it one way, but groundwater is largely hidden from us. We can't directly see groundwater often, except for where it comes out in springs. And so we tend to think of it as a separate system. And many states even have different regulatory regimes, different rules, different laws, even different agencies that regulate surface water and surface water quality versus groundwater and groundwater quality. So even in many states, they're treated as separate systems in terms of laws and regulations. But in fact, groundwater and surface water are really one system. We've learned this earlier in the semester. I've shown you this slide earlier in the semester when we talked about hill slope processes and infiltration and percolation. Water falls on the landscape and it infiltrates and it comes down. Some of it becomes part of the aquifer, gets below the water table, and that water table then is directly connected to surface streams, and the base flow, the day-to-day flow in those streams when it's not raining, is largely being fed by that groundwater. Some of it also comes from shallow flow through the soil, and then when it rains really hard, there's actually overland flow that may flow directly into the stream. But the day-to-day base flow is largely dominated by groundwater contributions. So it's arbitrary. It's not completely arbitrary. I mean, surface water is a little different than groundwater in terms of the function. Streams, to understand streams, we have to understand stream hydrology and stream geomorphology, like we talked about in the previous module. And there are different concepts we need to understand for groundwater, but that doesn't mean that they aren't part of one system. They're really the water system on our landscape. All right, and then another concept we talked about earlier in the semester, but I want to emphasize this because it's really important, is the hyporheic zone. So the hyporheic zone is this interface where the surface water and the groundwater interact, where groundwater moves into the stream, and even stream water can move into and out of the shallow part of the stream bed and the shallow part of the aquifer, and there's lots of exchanges there. Just like anywhere that you have two different sort of landscape elements mixing. Think about an estuary. What's an estuary? An estuary is where fresh water from a stream system meets salt water from the ocean, and you get something that's not quite salty and not quite fresh that's in between. And so you have a whole different ecosystem there, and often these ecotones, these intersections or boundaries between two distinct ecosystems, are some of our richest, most diverse ecosystems, where we have these interactions between two different parts of the landscape or two different elements of the hydrologic cycle. So the hyporheic zone in many streams and rivers and places has its own flora and fauna. It has a separate flora and fauna from the surface water or the groundwater proper. These are animals mostly, but even some plants potentially, that are able to extract the nutrients and energy sources that are being exchanged back and forth between these two distinct parts of the same system. All right, so that wraps up our first lecture on groundwater, about some of the fundamental concepts in groundwater geology or hydrogeology. We'll continue with the next lecture to talk in more detail about aquifer characteristics and some water resources issues in aquifers. So I'll see you then.